amazing ripples. I'm sorry to turn everything back to science,
But Judy, everything is about science.
exactly. So let's learn a bit more about waves.
Today we're going to talk about diffraction, which is the bending of a wave. But first, let's remember a bit about transverse waves.
A wave is a transfer of energy. If the wave is in a medium, the energy travels by means of vibrating particles. A transverse wave is one in which the particles vibrate at right angles to the direction in which the energy is moving. Let's revise some terms. Amplitude is the maximum displacement of a particle from the position of rest. A crest and a trough are the highest and lowest points that the particles reach from rest. The wavelength is the distance between two particles in a wave that are right next to each other and in phase. Remember that particles in a transverse wave vibrate at 90 degrees to the direction in which the wave moves.
Let's get back to the ripples. What we find interesting is that the stone hits the water once. But why so many ripples? Well, the stone starts many particles moving up and down, like your hand moving the slinky side to side. The energy passes through the slinky, eventually making all the particles move side to side. In the water waves, this energy is passed along to other water molecules, which then also move up and down. If we look at this from the top, each particle moving up and down makes a new circular wave.
Draw a tangent on every circle, and then put the circles next to each other and very close to each other. When the front edges of the waves are close together, they form a straight line which is exactly in line with the tangents. This straight line we call a wavefront. Take the tangents away to see the straight line at the top. But to make those wavefronts, the particles have to be doing exactly the same thing at exactly the same time. When this happens, we say the particles are in phase.
Now we're ready to define a wavefront. A wavefront is an imaginary line that joins a set of particles next to each other in a wave that are all in phase. When the object making those waves is straight, the wavefronts are straight lines. Each line usually represents a row of crest. The arrow shows the direction of movement of the wavefronts. When the object making those waves is a single point, like the stone, the wavefronts are circles. The arrow shows the direction of movement of the wavefront.
Now each point on that wavefront keeps moving up and down, causing more little waves, and in turn more wavefronts, and so it goes on. Because the little waves are only part of the big wavefront, they are called secondary wavelets. Each new wavefront keeps all the little secondary wavefronts together, like putting something in an envelope. If you put lots of small things into an envelope, then you can only see the envelope. In the same way, when the secondary wavelets come together, you can only see the bigger primary wavefront.
A scientist by the name of Christian Huygens put this into words for us. Every point on a wavefront acts as a source of secondary wavelets that spread out in all directions at the same speed as the wave. A new wavefront forms, which is the envelope of all these wavelets and at a tangent to all of them. To show diffraction, we are going to use a ripple tank. A ripple tank is a plastic tray of water with a light above it. The patterns in the water show up on a piece of white paper underneath the tank. First, we create straight wavefronts by making a straight object vibrate in the water. The waves look like this, and we draw them like this.
Now we put an obstacle in the water. See how the waves bend around the edge? This is called diffraction. We draw the wavefronts like this. Diffraction is the bending of a wave as it passes around the edge of an obstacle. It does this because the small secondary wavelets can spread out and form a new curved wavefront. Now, if you put two obstacles in the water, they create an opening. The waves curve on two edges now, so it looks a little different. Here is the diagram for that.
What will happen if you change the size of the opening? As the opening gets smaller, the wave is diffracted more and more until eventually the wavefronts are circular. So, the smaller the opening, the greater the diffraction. Let's see what happens if we change the wavelength of the wave.
As the wavelength increases, the diffraction increases as well. So, the longer the wavelength, the greater the diffraction.
Sound and light are both waves, so they should both be able to bend around an opening. So how come I can hear a person behind an open door, but I can't see them? The wavelength of the light is much smaller than the width of the door, so the amount of diffraction is impossible to see.
And the wavelength of a sound wave is bigger, almost the same as the width of a door.
Light can only bend around an obstacle if the size of the opening is very small.
In fact, about 400 to 800 nanometers. Remember, a nanometer is the same as 10 to the power minus 9 meters.
That is really, really tiny. Take a look at the meter ruler. If we divide this meter ruler by 10, you'll get 10 to the power minus 1. If we divide this again by 10, you'll get 10 to the power minus 2. If we divide this again by 10, you'll get 10 to the power minus 3. Now carry on dividing by 10 until you reach 10 to the power minus 9.
To show the diffraction of light, it is best to use a monochromatic light, like a laser.
Remember that monochromatic light is light of only one frequency and thus only one color. What we do is take a piece of black cardboard and with a sharp blade cut a thin slit into it. Shine the laser through the slit and onto a wall behind that. We get a broad red band in the middle with alternating dark and red bands on either side of it. This is explained by Hagen's principle. You can see the interference pattern on a ripple tank. The broad red band in the middle is where the light goes straight through the slit. On the sides, the secondary circular wavelets cause constructive and destructive interference. You will learn more about interference in the next module. So that is where the dark and red patches come from.
There is a relationship between the position of the dark bands, the size of the slit, and the wavelength of the wave. They all affect one another. We number the dark bands from the center outwards on both sides, like this. The first two are numbered 1, the next two are 2, and so on. These numbers have the symbol M. The angle theta is the angle between the straight line through the slit and the dark band. The relationship is given as follows. Sine theta is equal to M multiplied by lambda, all divided by A. Remember, M is the number of the dark band, lambda is the symbol for wavelength, measured in meters, and A is the width of the opening, also measured in meters. The whole point of the calculation is to show that the smaller the width, the greater the diffraction, and the longer the wavelength, the greater the diffraction, as we saw earlier.
So, let's look at the example that you'll find in your learner's guide. Calculate the angle of diffraction of the first dark band when red light of wavelength 690 nanometers passes through a slit of 6 micrometers. First, get your information right. M equals to 1, lambda equals to 690 nanometers, and A equals to 6 micrometers. Sin theta is equal to M multiplied by lambda, all divided by A. M is 1, lambda is 690 times 10 to the power minus 9, A is 6 times 10 to the power minus 6. Sin theta is equal to 0,115. Therefore, theta is equal to 6,6 degrees.
How will the pattern change if we use blue light instead of red light? It has a shorter wavelength. Let's do a calculation like that.
Consider blue light of wavelength 460 nanometers passing through a slit of 6 micrometers. Calculate the angle of diffraction of the first dark band. Sin theta is equal to m multiplied by lambda divided by a. So, sin theta is equal to 0,077 and theta equals 4,4 degrees.
So the angle is smaller. For red, it is 6,6 degrees, and for blue, 4,4 degrees.
Blue light has a higher frequency and therefore a shorter wavelength than red light. We've already seen that the shorter the wavelength, the smaller the amount of diffraction. That is why the central band for blue light is narrower than that of red light.
Could we have predicted this using our formula? Let's take a look. Lambda is smaller and it is in the numerator. This means that sin theta will be smaller and so theta is smaller. Let's try a typical exam question. Red light of wavelength 670 nanometers is shown through a narrow slit of width 20 micrometers and allowed to fall onto a screen. Describe and draw the pattern seen on the screen. A broad central bright band is seen with alternating dark and light bands on either side. The bands on the sides are less bright and narrower than the central one.
Calculate the angle between the second dark band and the central band. The first thing to do is to draw a diagram of the situation and write down all the information given. M equals 2, lambda equals 670 nanometers, A is equal to 20 micrometers. Remember, a micrometer is 10 to the minus 6 meters. Sin theta is m multiplied by lambda divided by a. So sin theta is equal to 2 multiplied by 670 times 10 to the power minus 9, all divided by 20 times 10 to the power minus 6. Sin theta equals 0,067, and thus theta is equal to 3,8 degrees.
Here are some applications of diffraction.
Diffraction is very important in the transmission of radio waves. Medium and long radio waves have a long wavelength and can thus diffract around mountains and hills and can therefore be received easily by people. However, they can only travel about 100 kilometers. Short radio waves don't diffract enough to follow the curve of the Earth and are bounced off the ionosphere. They can travel very far. Microwaves, which are used for TV, have very short wavelengths and no diffraction. These can only be transmitted in a straight line. Towers are used for transmitting and receiving signal.
Another example is a shadow cast by the sun on the ground. From a distance, the darkened part of the shadow looks like a sharp line. Instead, there is a blurred area along the edge because the light was bent or diffracted at the side of the object. There is also a little device called a diffraction grating that can be used to form a spectrum of light. It has tens of thousands of tiny slits built into it. It turns a beam of white light into a spectrum. This happens because each slit of the grating diffracts the beam slightly differently, so that the colors can be seen separately. This is used to study the structure of atoms and molecules and to find out what stars are made of.
Yes, you got it right. Finally, you got it right the first time.